Our second speaker is Han Zhang from Suzhou University. He will talk about Khintchine's theorem for self-similar measures. So Han, please.
Okay, thank you very much for the invitation. And today I will talk about my joint work with Timothy Bernard and Wei Fenghe about the Khintchine theorem for self-similar measures. And Timothy is a researcher in CNRS, and Wei Kun is also a researcher in Chinese Academy of Science. So today's talk is mainly about the Diophantine approximations for self-similar sets. Okay. First of all, let me introduce the classical Khintchine theorem for you. And to do that, let me first introduce a few notations. So first of all, let me fix a non-increasing function psi from natural numbers n to non-negative reals. And we often call this kind of non-increasing function approximation function. And then we take a real vector S in the Euclidean space Rd, and we call such a real vector X psi approximable if we can find infinitely many integer vectors PQ, such that the supreme norm of QS minus P is less than psi Q. So if this inequality holds for infinitely many integer vectors PQ, this roughly means that my real vector S can be approximated by many integer vector P over Q with the speed of psi Q over Q. It essentially tells me that whether or not a real vector S can be approximated by a rational vector with a certain speed. Okay, so then we can collect all these psi approximable real vectors S in Rd to form a set, the W psi. And one of the main goals in the measured number theory or the theory of Diophantine approximation is to study the dependence of the size of W psi on my approximation function psi. Okay, so it is well known that by the theorem of the Dirichlet, if we know that psi q is greater or equal to q to the power of -1 over d for all q, then we can easily conclude that W psi is my whole Euclidean space Rd. Now the question is that what happens for other general approximation function psi? Okay, so then a theorem proved by Khintchine in 1920s give the following surprising results. So we fix a non-increasing approximation function psi. Then Khintchine proves that the Lebesgue measure of W psi intersects the 0, 1 to the power d unit cube. Is either equal to 0 or equal to 1. It is 0 if the psi q to the power d is summable or is convergent. If this series is divergent, then the Lebesgue measure is equal to 1. Okay, so Khintchine's results tells us that we have a 0, 1 law of W psi in the sense of Lebesgue measure. Okay. And also, we know that in the Khintchine theorem, we need to assume that my psi is a non-increasing function. This assumption, non-increasing, is very crucial. If you remove this non-increasing assumption, then it becomes another problem. Okay, so in this talk, we all assume that our approximation function is non-increasing. All right. So now there is a natural question that if we replace the Lebesgue measure in the classical Khintchine theorem by other natural measures on Rd, we can ask whether or not the Khintchine theorem still holds. So by other natural measures on Rd, I mean that, for example, you can take the natural volume measure supported on certain nice submanifold on Rd. Okay. That is related to the Diophantine approximation on submanifold on Rd, which is also a very important research field nowadays. And another class of natural measures is given by the self-similar measures on RD. Okay. And a simple example for that is that we can, I'm sorry. A simple example for the self-similar measure is that we can consider the middle third Cantor measure on R on the real line. Okay, and indeed, this middle third Cantor measure is motivated by a famous question of Mather in 1984. So Mather, in his suggestions for future research in 1984, asked the following question. So how close can irrational numbers of the middle third Cantor set be approximated by rational numbers not in this middle third Cantor set? Okay, so Mather's question actually motivated Kleinborg, Lindenschutz, Weiss asked the following question in the year 2004. Okay, so they consider a conjective irreducible self-similar measure sigma on RD, and suppose this self-similar measure also satisfy the open set condition. Then given any non-increasing approximation function psi, Kleinborg, Lindenschutz, and Weiss ask whether or not the classical Khintchine theorem holds for this self-similar measure. So that means that we still have this 0-1 law of sigma of W psi. Okay, so what we did here is that we only replace the back measure in the classical Khintchine theorem by a self-similar measure sigma. Okay, and ask whether the same conclusion holds. Okay, so there is a simple remark here is that the Lebesgue measure or the Cantor measure are all self-similar. Okay. So actually, Kleinborg, Lindenschutz, Weiss asked whether we can generalize the classical Khintchine theorem to all the self-similar measures. Okay, any questions so far? Okay, let's move on. So to introduce self-similar measures, let me first recall some background on iterative function systems and self-similar measures. So for that, we denote sim plus RD to be a subgroup of all the affine maps from RD to RD, such that any element phi in this group sim plus RD can be written as phi s equals R phi times O phi s plus B phi. So where R phi here is a positive real number, and O phi is a rotation matrix in the Lie group SODR, and the B phi is a translation vector. Okay, so that means that any element in sim plus RD is a similarity maps. Okay, so then a self-similar iterated function system is a probability measure lambda on this group sim plus RD. Okay, so by the classical result of Hutchinson and Bourgeois-Picard, if we assume that this IFS lambda is conjective in average and also has a finite exponential moment, then we can find a unique finite matrix sigma on RD such that lambda convolved with sigma is equal to sigma, meaning that my sigma is stationary under the action of lambda. Okay, so then we call such measure sigma a self-similar measure. Okay, so so here in these assumptions, we need to assume that my lambda is conjective in average. That means that we can allow some contraction ratio R phi to be larger than 1, but on average, the top Lyapunov exponent is negative. And also, this lambda need to have a finite exponential moment. It means that maybe the support of lambda is infinite, but we need to have some control on the support of lambda. Okay, it cannot be very weird. Okay, so now let me give you some examples on self-similar measures. The first one is the classical example, the middle third Cantor measure supported on the middle third Cantor set. Let's this is the natural Hausdorff measure supported on the middle third Cantor set. And the second example is the two-dimensional example. We can take the Hausdorff measure on the Sierpinski triangle. And the support of this associate IFS lambda has three affine maps, phi 1, phi 2, and phi 3. Okay, and this measure lambda put equal mass on all of these three maps. And the following is the picture for the Sierpinski triangle. So to construct this kind of triangle, basically you start with a equilateral triangle, and then you remove the open middle third part of it. Then you have three smaller equilateral triangle left. And for each of these smaller equilateral triangle, you do the same thing. You remove this middle open third part of it. Okay, then you keep doing this over and over again. And then you intersect all the set you obtained in each step to form this Sierpinski triangle. Okay. So then its natural Hausdorff measure is our is an example of self-similar measure. Okay. Okay, so then in this slide, I will give a quick survey about some previous results for the about the Khintchine theorem for self-similar measures. And these results are certain partial results in the sense that all these results need to assume either special self-similar measures and or very special approximation functions. In particular, we first look at the convergence case of Khintchine theorem, meaning that the series of psi q is summable. And Weiss was the first person to obtain the convergence Khintchine theorem for the middle third Cantor set in 2000, in the year 2000. But Weiss result need to assume certain very special approximation function. And later in 2004, Kleinberg, Lindenschutz, and Weiss generalized Weiss result to the higher dimensional case. But they also they are also only able to deal with the convergence case of the Khintchine theorem, assuming some special approximation functions. Okay, so for the divergence case part, Angela, Fishman, Shapila in 2011, they were the first to obtain some results for the divergence Khintchine theorem for the middle third Cantor set. Okay, and then Simons Weiss later in 2019 generalized Angela, Fishman, Shapila's result to the higher dimensional case. They were able to handle the divergence case for a large class of self-similar measures in the higher dimensional case, but still their approximation function are very special. Okay, so recently there was a major result in this direction proved by Khalil Luthi in 2023. So in their result, they were able to prove Khintchine theorem for any non-increasing approximation function psi. However, their self-similar measure sigma need to be restricted to certain very special class of the whole self-similar measures. Okay, meaning that they need to assume that the self-similar measure sigma is associated IFS lambda is irreducible, conjective, finitely supported, and large dimensional, rational, and also satisfy the open set condition. Then given any non-increasing approximation function psi, they obtain the full analog of Khintchine theorem, meaning that we have this 0-1 law holds for sigma of W psi. Only depending on whether this series convergence or not. Okay, So in that result, I need to explain a few words about these two actual assumptions, large dimensional and rational. So large dimensional roughly means that the Hausdorff dimension of support of sigma is close to D. The ambient space has the dimension D. They need to assume that the support of sigma has the dimension very close to D. Okay, and the rational means that all the parameters in the affine maps in the support of lambda need to be rational. Okay. So for example, the middle third Cantor set is not large dimensional in the sense of Cayley-Luty because it's not very close to 1. Okay. The dimension of the middle third Cantor set is log 2 over log 3. It's not very close to 1. And also, if you consider any irrational translations of the any irrational translations of this middle third Cantor set, and then take the Hausdorff measure supporting on that, then it is not rational, okay, because the is associated self-similar IFS lambda is not rational. So some parameters there is irrational. Okay, so as a consequence, Cayley-Luty's result does not work for the middle third Cantor measure or any irrational translation of it. Okay, so even though their results cover a large class of self-similar measures, but due to these two additional assumptions, large dimensional and rational, so they didn't obtain the full analog of the Khintchine theorem for all class of self-similar measures. Okay, so now we want to either remove some actual assumptions of Cayley-Luty's result or relax some assumption of their results. Okay, so the following is our main result in Khintchine theorem. So we consider a self-similar measure sigma on RD and assume that its IFS lambda is irreducible contractive in average with a finite exponential moment. So then, given any non-increasing function, non-increasing approximation function psi, we obtain the full analog of the Khintchine theorem for sigma of W psi. We have this 0-1 law depending on whether this series convergent or not. Okay. So as I said, we remove the three actual assumptions in Cayley-Luty's result, meaning the large dimensional assumption, rational assumption, and also the open set condition assumption. And also we relax the contractive assumption in Cayley-Luty's result to contractive in average, and finally supported to a finite exponential moment. Okay, so because we don't require any other assumptions on the self-similar measure sigma, so our theorem works for the middle third Cantor measure. And also all the self-similar measures considered in the question of Kleinborg-Lindenstrauss and Weiss. Therefore, the questions of Mother and Kleinborg-Lindenstrauss and Weiss are resolved. Okay, so one remark for this main theorem. So in 2024, last year, we were only able to handle one-dimensional case, D equals 1. And in this year, we extend our previous results to all the dimensions, D greater or equal to 2. Okay. Any questions so far? Okay, so now let me explain how we prove such a number theoretic result using the dynamics on certain homogeneous spaces. Okay, so we use some dynamics to prove such a result. In particular, we look at the Lie group G equals SLD plus 1R, and we consider a discrete subgroup gamma equals SLD plus 1G in the Lie group G. Okay, then we take the quotient space X equals G mod gamma. And we often call this such a quotient space G mod gamma the homogeneous space of the Lie group G, because it estimates a Lie group action G. Okay, G can act on the quotient space X by the group multiplication. Okay, and it is also well known that this quotient space X can be identified with the set of all unimodular lattices in Rd plus 1. So this identification is by the group action of G on the unimodular lattices. It is easily seen that this action is transitive, and the stabilizer of the special unimodular lattice GD plus 1 is the subgroup gamma equals SLD plus 1G. Okay, so through this identification, so we give this quotient space X some number theoretic meaning. Therefore, we can use the dynamics of G acting on quotient space X to study certain Diophantine approximation problem. All right. Okay, so then in this Lie group G, we consider the following two special subgroups. The first one is one parameter diagonal subgroup AT, which is written in this way. It consists of certain diagonal matrix. And then we also consider a subgroup of the upper triangular matrix. So we take for any real vector S in Rd, we vertically embed this S into the last column of my D plus 1 times D plus 1 matrix to form this upper triangular matrix US. Okay. So now we want to study the dynamics of AT times UX acting on this quotient space X. So how is this dynamics related to the Khintchine theorem? So this relation is discovered by Kleinborg and Margulis in 1919. So in that paper, they show that the study of Khintchine theorem for self-similar measures sigma can be translated into a study of a shrinking target problem. So this shrinking target problem has targets being these shrinking cast neighborhoods in the quotient space X of the forward orbit ATUS gamma, where here S, I restrict this S into in the support of sigma. And I want to study how this forward orbit, when t goes to infinity, intersect this sequence of the shrinking targets. Okay, so the following is a simple picture for this shrinking target problem. So this large shape is my quotient space G mod gamma, and it is well known that G mod gamma is non-compact, so it has some cusp. So here in this shrinking target problem, I take the shrinking target to be this yellow shaded region, which is a sequence of the shrinking cusp neighborhood. So when this index sub-index t goes to infinity, this target will shrink to my cusp. So then I want to study how this orbit ATUS gamma, when I restrict my S into the support of sigma, intersects this sequence of the shrinking target. Okay. So it turns out that the resolution of this shrinking target problem will depend on certain effective equal distribution theorem for the expanding translate of fractals. Okay, so the following is our main theorem, main dynamical theorem. So we assume of sigma to be a self-similar measures on Rd, and is associated lambda IFS lambda is assumed to be irreducible contractive in average and has a finite exponential moment. Okay, so then we can So in our main theorem, we show that there exists a positive constant C depending only on sigma, such that for any given base point X in J mod gamma in the quotient space X, for any compactly supported and smooth function F on X and any t greater than 1, the integral of F along this orbit ATUS times X with respect to the self-similar measure sigma has the main term the integral of F with respect to the higher measure mx of the quotient space and then plus very explicit error term t to the power minus c times injectivity radius x to the power minus 1 times certain subleft norm of F. So this subleft norm is it's roughly this the C1 norm of F. Okay. So in this theorem, if we look at the error term here, when t goes to infinity, because c here the constant c is greater than 0, when t goes to infinity, the error term will goes to 0. Okay. So it means that my integral f with respect to this self-similar measure is almost equal to my integral of f with respect to the higher measure of the whole space. Okay. Or in other words, my orbit ATUS times x will equal distributed in J mod gamma when t goes to infinity. All right. So for this result, actually Cardio-Lucy, they also proved a weaker theorem in their paper under their actual assumptions for the IFS. Okay, so in our main theorem here, we just remove their actual assumptions. So therefore, we are able to handle a very general class of self-similar measures to obtain this Khintchine theorem. Okay, so in the last slide, I will say a few words about the proof of this equal distribution result. So in the first step, we used a key idea of Simon's Weiss in 2019 we can use their results and to induce certain associated random walk on X by the given self-similar IFS. Okay, so this random walk is on my homogeneous space X equal J mod gamma. Okay, so then we want to study the behavior of these random walks induced by IFS. Then it turns out that a key step in the proof will depend on certain multi-sliding theorem shown by my co-authors in their earlier paper. And this multi-sliding theorem can be viewed as a certain generalization of the Bourgain's theorem. Okay. And when D equals 1 in the lower dimensional case, the multi-sliding theorem can be easily applied in the proof to obtain the results. But in higher dimensional case, there are many complexities. In particular, there exist certain algebraic obstructions to apply this multi-sliding theorem. And what we do in the higher dimensional case is that we need to go into the Lie algebra of G and show that this kind of algebraic obstructions can be overcome by certain linear algebra trick and also some combinatorial tricks. Okay. So I will stop here. Thanks for your attention.